Hello everyone, I'm Giulio, and today I want to talk about MMO-CHIP, which is a project I'm working on, and the tagline is from Microscope to Verilog in 1 hour-ish, and let's dive into it. Just to start, you probably know me from other talks, but I like to reverse engineer all the hardware, especially when it comes to like music technology and video games. Why do I do this? Because there is like a lot of information that is buried into the silicon, into hardware, software that runs on specific platforms, but we don't know how the platform works, so we cannot emulate it and we cannot preserve it. If in 10 years, in 50 years, someone will want to play that video game or use that device, they won't be able to, because all of those are dead. But that's kind of sad, because since they're only run software, we should be able to perfectly replicate how they work. But because the platform is proprietary, we can. And I'm trying to preventing this loss from happening by learning and documenting how things worked. And this is also cool, because back then, they used a lot of cool tricks with the hardware and think about everything that they did to make video game possibles on MS-DOS, for example, or on gaming consoles. It would be very cool to keep this information around. And as I said, one thing that specifically interests me, it's emulating all musical instruments and effects, for example. Things like DSP chips, sample player chips, and some FM or algorithmic synthesizers. And I work with an open source group called The Usual Suspects, in which we're essentially taking those old devices, such as the Roland GP8000, and convert them into plugins for music production. Why? Because that way you don't have to find the old out-of-production hardware to be able to use those sounds. You can get the emulation plugin if you own the original unit, and use the original ROM that was running on those devices, and have a modern emulation that is like bit perfect, bit by bit, to the original hardware. But it also offers a lot of modern conveniences, like the ability to just have 10 of them at the same time, and the ability to easily modify your presets, for example. How do we do this? The classic approach is the black box approach, in which we try to figure out externally how those things work by using probing, for example, with a logic analyzer. And in case of DSPs and CPUs, a method that works really well is sending some test programs and seeing how the hardware reacts to them. For example, sending random bytes as program until something changes something in the CPU state, and figure out, that's one accumulator, that's the command for outputting, and stuff like that. So it's a lot of educated guesses and verification. It's a lot of formulating an idea of how the thing could work, and then running a lot of tests to verify that the assumption is correct. And this has worked really well, for example, for the GP8000, because we essentially figured out entirely how the bytecode for the DSP chip worked. And if you want to know more about how we did that, I did a talk at last Congress. This is an approach that worked well sometimes. Other times it just didn't. For example, I reverse engineer also this device here, which is a digital piano. And sometimes, like with the other chip, you get enough surface and enough inside knowledge to try to guess things, and those guesses allow you to start figuring out how it works. Other times, in this case, for example, the logic was so custom and so non-programmable that I just couldn't figure out anything from the outside. Like, there were a bunch of custom chips that were doing magic stuff, and those custom chips were not programmable, they were fixed function. So what do you do in these cases? One of the most common approaches here, it's the capping the chips. If you take those custom chips, you apply a lot of hot air or acid, you're able to remove all the epoxy that is around it. And for example, here, that's something that I did as a test without hair. And you can see inside that there is like that small piece of silicone, aluminum, and glass, and other materials, which is the dye. And that is what happens when you look at a dye like that on the microscope. I mean, you can already see some things with naked eye, but once you look them with a decent optical microscope, you're able to see a lot of tiny wires, connections, transistors, and stuff like that. And what can we do with it? What can we see on a chip once we magnify it with a microscope? This is an example of like one section of what you can see in a chip like that. This is a Fujitsu standard cell chip. And you can see that there are those kind of blobby areas in which a lot of things is happening. And those are called the standard cells. Essentially, those are small blocks that implement some specific logic function. And we are able to, the people were there back then that designed it, we were able to take those from a standard library, like how you would do with programming, and they will place those next to each other in a chip. And each one of those could implement a specific function. For example, those 4 small ones, those were NOT gates, inverters, that if you put a 0, they return a 1, and if you put a 1, they return a 0. The other 3, I have no idea, but I guess those are flip-flops, possibly, but I haven't checked. Then once you have those cells, they're connected to each other using wires. And those wires go from one cell to another and essentially make up a circuit. And those wires generally were made of metal, and the metal that was used back then and also now, it's kind of almost always aluminum. And if you think about it, then if you want to reverse engineer a structure like this, it's actually very similar to what you would do with a PCB. In a PCB, you can like take a picture, maybe even with X-ray of the PCB, and see where all the parts, the components, the resistors, the capacitors are, and those map really well to what the cells in a chip are. And then you want to trace all the traces and see how those components are connected together. It's essentially the same thing that you do with the wires in a chip. And the goal that you want to reach is that in a PCB, you want to have like a list of components and how they connect to each other. In a chip, you want to have a list of cells and how they connect to each other. Caveat, not all chips were made equally. This description with the standard cells and the traces is very specific to CMOS standard cell chips and gate arrays, which were kind of still like the majority of how that kind of those kind of chips were done back then. But this is like, there were other kind of stuff, but those were kind of the most popular ones. So I talked before about standard cell libraries, which is this idea of defining a bunch of logic blocks, such as, for example, that's an AOI, which means an AND with an OR and an inverter, or an AND gate, the opposite of an AND, or a multiplexer, which basically takes some input and some output and allows you to select which one you want. And that was a common way of manufacturing chips back then. You could define how those chips behave with code or with a schematic, and then you would give this code or schematic to a manufacturer that will use their standard library to generate a chip by placing those components around and connecting them together. And it's cool because back then those things were already, like even in the 80s and 90s, those things were being manufactured algorithmically. Like they started from some code description, and they had algorithms that placed all the cells on a specific grid and automatically generated like set of wires that with an auto router that connected things together. And so how do we go from this to actually having an emulation of this chip? So First, we need to recover the netlist. We need to recover where all the cells are and what they do. And we need to recover how they're connected together, which is like saying, on a PCB, we need to find out what is the full BOM, what are all the parts in the PCB, and how they're connected together. And we need to convert that into a logic circuit, put all of those cells into a circuit that we can understand what it does. And once we have that, we can reconstruct code in some language for hardware description, like Verilog, that essentially allows us to either emulate the entire thing or look at it and try to guess what those things might be doing. This is the workflow that I essentially used so far to reverse engineer the chips that I did, which it's basically based around Inkscape for annotating stuff, exporting to SVG, and then processing those SVGs with a bunch of custom scripts. It was not great, but it kind of worked like that. First, I imported the image into Inkscape as a background and locked it so that I could use it like as a guide to draw my annotations. Those images are basically gigapixel images. Those have like 300 megabytes of JPEG, which means that once you convert that to bitmap, it's going to be huge. And then what you do is that you want to draw all the wires as a polyline. You can use the line tool, like the pen tool in Inkscape, and click, 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 and annotate all the wires. And then once you do that, you can mark each cell with a rectangle. In this chip, all of the cells were laid down on specific rows and columns. And so what I did is that I went through each one of them and drew a rectangle around it, so that way I could annotate where each cell was. And then I run my bunch of very poorly written script in JavaScript. What I did is that they essentially loaded this SVG with all the annotations and found all the rectangles of the cells. And once we have that, we can just use those rectangles as crops for the image. And basically, I exported every single cell as a JPEG. And this is the most efficient kind of way that I found to do this, because once I do that, I was able to find all the cells that looked similar and put them in different folders, so that I had one folder per cell type. And one interesting thing is that if you sort those images by size, by file size, you can find all the ones that are similar physical size, because the image will be the same kind of amount of pixels. And that kind of helps dividing them a bit further, because you know that if a cell is like this and then another cell is small, they cannot be the same cell. And so this was a bit of a manual process that took several hours, but that was better than annotating stuff directly in Inkscape, I guess. And then we're still at the point in which we need to find out what those cells do. So I basically created a catalog with the help of the info from a lot of other reverse engineering people. And for this kind of chip, I found all the possible cells and cataloged them in a spreadsheet. And then I run also another script that used all the annotations for the cells and all the annotation for the wires and produced code. I did a talk at the 38C3 about how this worked, but essentially it went through all the cells and found all the wires that were geometrically intersecting the cells and used those intersections as like input and output. And once you have that, you can plug that into what is your logical function for the cell, if it's an AND or an OR, and you can basically output a list of cells and a list of what are all the Boolean functions for each ping. And did this work well? Kinda. This was my first experiment in reverse engineering chips, and I managed to reverse engineer like those 3 chips for that digital piano thing, and it took a lot of time, and I learned a lot by doing that, but there are a lot of things that were incredibly painful, and I don't want to do that again in that way. One problem is that Inkscape, it's a great software, but somehow it really hates when you put big images, because it internally probably converts that to a raw bitmap, and but that still doesn't make sense because it doesn't seem to be taking too much RAM. There is no clear way to change what is the RAM limit of Inkscape. So if you put any image which is bigger than 400 megabytes, it just crashes. And I would be forced to reduce the size, but then if I reduce the size, I lose the resolution and I can't see things anymore. For example, that image is almost 1 gigabyte, so that would have been completely impossible to put into Inkscape. And this was one of the big problems. Another problem is that Inkscape, it's like meant for artistic drawing. It's meant for doing vector graphics, not really for annotating stuff. So it's not really great for annotating wires on a chip. One example is that if you look at that thing there, you have that wire that bifurcates. You have a connection that goes in one direction and one connection that goes in another direction. That's very common even in PCBs. You have one wire that goes to a lot of stuff. So wires are a graph. They're not a simple line. And you cannot have graphs in Inkscape. And so what I used to do in the situation is that either I would draw the wire and then draw another wire to go back and continue, or I would have to draw multiple things and then group them together. Sometimes I would just forget to group things because you had to keep track of that manually, and then I would result in things that electrically didn't make sense, and I stay there for several hours trying to figure out what is going on. Then, if you look there, you see that there are a lot of wires that are just parallel. It would be really cool to have some kind of multi-drawing tool, like to be able to draw multiple wires. KiCad allows you to do that. Inkscape is not meant for drawing wires, so you cannot do that. And you can add metadata on Inkscape on stuff, but it's not really structured, and it's not really meant for that. And so that was another problem. If I wanted to, for example, add the information of what layer a specific wire was, I couldn't really do that. And another thing that really freaked me out is that at least on Mac, the line tool cursor is not calibrated. You would expect that cross thing to be where the wire ends. It's not. It's a few pixels off. And every time I basically built some muscle memory to take that into account. And I don't want to go through this misery. And another problem, this is a skill issue of mine. My tooling was a mess. I was basically hard coding a lot of stuff and multiple scripts because I was experimenting while doing this. For example, the name of the files and all the pixel sizes. And it was even difficult to visualize this kind of stuff because like in those scripts, I needed to like enter some pixel values that I had to copy paste manually. And that was not great to figure out when specific problem came up. Another problem is that, yeah, we can recover the list of cells and how they connect together, but when it comes to the actual cells, it was still a problem to reverse engineer them. Because you will need to basically take a screenshot of the cell, put it into Inkscape or something, and see where all the layers and the transistors are, and then manually copy that into a schematic or create a list, put that into like a circuit simulator, and it's doable. Like if you have some simple cells like those, like that's an AOI, like 2 ends and a NOR, or an inverter there. But if you get some more complicated cell, like this is a 4-bit adder, in which you have like 150 transistors, you will need to trace it entirely manually, and then copy the entire schematic manually, checking where all the wires connect to each other, simulate it, and if you did anything wrong, then you will need to recheck everything. It was painful, and I'm trying to find a way to maybe automate this. And so I asked myself, can we do anything better than this workflow? And I started looking around for a few maybe existing tools, because someone had to solve this already. cannot be that I'm the first one. I mean, I'm doing something very niche, but that's another topic. I found one tool, which is called Digate. And I don't want to talk too bad about it, because I couldn't figure out really how it worked. The build for macOS, it's not really updated anymore, and it seems to not be too much maintained. And I heard people talking very well about this thing, but it doesn't seem to be too great for tracing big chips. Like, I couldn't figure out how to do that with Digate. And there is another tool that is in development right now called the drout from some other people in reverse engineering. This has been being working on by a group called Emo Russia, that they're using this to reverse engineer some chip on the PlayStation 1, which is a lot of a bigger task. And it's essentially built exactly for this kind of work. The problem is that it's kind of Windows only, because it's written in .NET. And it's a great tool, but it's still a bit kind of custom. Specifically in their description, they say that this is meant for cheap reverse engineering people, so it's going to look incredibly unapproachable by people that are not into that. And I tried to use it, and it's cool, but there are still some things that I wanted that were not there. And but I want to give the special mention to how they have a counter that tells you how much work you spent there. And if you idle for a bit, it tells you that, which is kind of endearing. And everything else seems to be completely proprietary or custom internal. I looked around, and it seemed like that companies that specialize in this build their own tools. But apparently, even if they build their own tools, it's like a bit of a glorified Inkscape that doesn't seem to have been too automated, this thing so far. So we cannot get those tools, of course. This is probably a bit of an example of companies developing the technology to do that and then keeping it as secret as possible, especially since it's such a niche thing. And the open source community building stuff, but of course the open source community is built by people that have limited time after their job, so we do our best. And at this time I ask myself, is it time that really I should build some tooling for this? The complexity in my projects was rising a bit, as I've shown before. There were some chips that were like 1 gigabyte of picture, and it was still not, Inkscape didn't work anymore. And I also wanted some features that are not there yet, like some UX that worked a bit better, like some more modern shortcuts and stuff, and some maybe computer vision and machine learning features, because we have those. Why do we have to do everything manually where we have modern vision models that can maybe do something for me? And another thing I wanted to try is multiplayer, because if we are in an open source community with a Discord server with 10,000 people, there must be at least someone that I can just give them a link and have them draw some wires. And so I built this. This is the tool that I built. I called it MMO-CHIP. Why MMO? Because it's web-based and collaborative multiplayer. You can just give a link to someone, if you have a deploy, and have them collaborate on your chip and draw wires and annotate cells for you. And it's really fast. I spent a lot of time making sure that the UI actually responds quickly enough. And there's still some work to be done, but it's decent. And it has a lot of features that are especially designed for annotating cells and wires and stuff. So it's not like a generic drawing tool, but it's a very specialized one that uses data models inside that are specifically for this. And the cool thing is that at the end, it doesn't just output the annotation, but it's end-to-end. It's able to output Verilog code that you can start refactoring and reverse engineering and maybe even simulate. With some limits, but we're getting there. And it's essentially a big React app with a Node.js backend. And it also has a machine learning part that it's built with Python. So it's essentially like a front end and 2 backends that are communicating with each other. And for now, I took the incredibly lazy approach of saving everything in a bunch of JSON files, essentially, since I'm the only one using this locally for now. But eventually, we'll have to move this to a proper database. And it supports huge images. This is a problem that we had with Inkscape before. And how do we do this? When you load a new die shot, the picture of a chip, it automatically starts splitting it into a pyramid of different levels of zooms, and so small tiles that we can stream from the network or from the disk, which is essentially also what Google Maps does. You don't load the entire globe, but when you zoom in, you automatically stream the tiles that you need. The pan and zoom, it's both trackpad and mouse friendly, because I'm a weird Mac user that hasn't used the mouse in 7 years. So I can just use my trackpad to move around. So I can technically even do this while riding public transport. No more out of memories, because we have this system. And the annotations that you can render on top, they're also rendered on tiles, which is a rendering approach that is kind of similar to what Figma does, for example. Since this is all done with JavaScript canvas, we are rendering all the possibly millions of annotation in a lot of small tiles. And every time we are filtering what goes in each tile so that we don't have to render too much while panning around. And let me show you a bit how it works. So this is our tool. And we can move around the chip, and we can zoom in and zoom out. And we can try to draw some wires. We can, for example, go here and draw a wire here. And let's find, for example, one that actually bifurcates. Oh, this one here. Let's suppose that we're drawing this one. And we press enter. And you can see that like the wire, when I zoom in and zoom out, it stays like in screen space, so that I'm able to keep it at the same width in every zoom, so that it doesn't necessarily become invisible when I zoom out. And I'm able to do midpoint rounding. I can just click whenever, and this will keep the entire net connected. I can click on a single wire, but I can also double click, and it will highlight the entire thing. So every time that like I start in the middle or I continue a wire, I don't necessarily have to do the entire regrouping ordeal that I had to do before, but I can just continue to move stuff, continue to extend the wires. Another cool thing is that the undo, it's completely like dependent on what mode I'm in. So if I press undo, I just undo the drawing in the current mode. But if I undo without drawing, I just remove the last stuff that I did. And so this is how it works with the wires. And I'm also able to do stuff like drawing cells. For example, I can go here and annotate this cell here. And what will happen is that then I will like automatically have this cell in all the other modes as well. I don't need to crop it manually. But you can see that like this chip follows a bit of a regular pattern, and we can have guides. We can set a guide here and here, and then we're able to just copy those guides and copy them around, so we can build the guides for everything in just a few seconds. We can move them later. We can select and duplicate. I'm pressing Option and dragging them so that like we have all the shortcuts that you will normally get on like graphics software. And now we're already done. And we can also place like a vertical and horizontal one, but let's just do the vertical one for now. And let's start to annotate some cells. For example, this one here, and automatically snaps. And let's find another one. For example, this one. This one here. And let's do just another, just for test. Let's see. Normally I would like go through the entire chip and do everything, but now we can just do some for test. And this one here, just for fun. Okay, and at this point we already started annotating some cells. Probably also want to draw some wires later. And another thing that we have is called the merge cell, which is what I called Tinder for standard cells. The thing that I want to do before is automatically that I need to merge the cells that look similar. And here we can just, for example, go through all of those and see that this one is essentially the same. So we can also check with the difference. And we can merge it like this. And then they become the same cell. And then we can go into reverse engineering cell. Let's try to do this. We should draw the diffusion. And then we can draw the polysilicon, and so on. And once we draw all of those things, that now I'm not going to do because it's going to take some time, we automatically can find what kind of cell this is. Just by looking at all the layers that make up the chip, we can already figure out what kind of cell this is. And this works for simple cells, but also for more complicated ones. And not only we can have a schematic of how the entire cell works, and also we can have like a logic schematic that shows us what is happening internally in the cell. And so, as I showed, like we have this kind of die inference pipeline that I forgot. At the end, we basically also have code. If we annotate an entire chip, like I did here, at the end we already have some Verilog code that we can see, and we basically have already like some Boolean formulas for a bunch of things that we're interested into the chip. So, how does this work? As I said before, we start from the die annotations, and with that we can get our netlist, how the cells are connected together. We have our cell annotation, with which we can find out all of the cell types. And we basically plug all of this into a big expression and AST simplification, which at the end generates code for us. And the fun part is what's happening here. How are we able to essentially get those annotations and convert those into cell types and figure out the Boolean formula? To explain this, we need to go back a tiny bit, and we need to talk about MOSFETs and how CMOS works. You essentially use transistors to build those kind of cells, and you can have PMOS and NMOS transistors that they work the same way but inverted, and they act as switches. If you apply a logical one, some voltage to them, they either pass electricity or not. And this allows us to, for example, implement what we have here, which is an inverter. If that's 1, the output is 0. If that's 0, the output is 1. And those are arranged in what is called like a pull-up and a pull-down network, in which all the pull-up network, it's built of PMOS transistors, and that's the thing that keeps the output to be 1, and the pull-down network, it's what makes the output be 0. And those are always complementary, and so they implement the exact same thing, just inverted, so that one can put a logical value 1, and one can put a logical value 0. And if you see here, you see that, for example, in the pull-up network, the output is true only if all of those input is true, because they're connected in series. So you basically get this Boolean formula, and the pull-down network, instead, it's in parallel. And if it's in parallel, it's an OR, because it's enough that one it's true to be pulled down. And you can see that those are exactly complementary, and that's how CMOS is built. And with this, we can already figure out that this is a 3-input NOR gate. But how is this actually built into the chip? You have multiple layers that are made of different materials. One is the diffusion, which is the background of the transistor. It's basically a doped P or N area that forms the transistor source and drain. And this polysilicon, those lines, which it's made of a slightly different material, which make up the gate. And then we have the metal and the vias, which are connections. It's equivalent of traces in PCB. And the vias are what connects multiple layers together, or a specific layer to the diffusion or polysilicon. And this is a bit how it works internally. If you have some diffusion and a gate made of polysilicon or metal on top of it, that's what makes a transistor. Essentially, you can see there that specific area is one single PMOS transistor, in which you have one source, which is connected to power, one drain, which is connected to something else, and that green line of polysilicon, which makes the gate. So essentially, every time that you have a crossing between a polysilicon and diffusion, that essentially makes up NMOS or PMOS transistor. Is there more? Yes. You have transmission gates, pass transistors, which can be used to implement all sorts of fun stuff, but we're not talking about that today, because otherwise this would become a lecture in CMOS. But I want to talk about how the actual algorithm for inference works. The idea is that, as I said, every time that you have a crossing between polysilicon and diffusion, it generates a transistor. So the first step that we do is that we use an algorithm called Clipper, which is an algorithm for clipping polygons and performing Boolean operations. And we're splitting the diffusion into source, drain, and the gate. And that way we can figure out where all the transistors are, because as I said before, a transistor is every time that you have some gate crossing diffusion. And once we do that, we can compute the nets. We can use the unifying algorithm and see where all the shapes overlapping. And that way we can reconstruct a netlist. For example, seeing that something connects to ground, something to power, some diffusion connects to some other metal parts, and so on and so forth. Once we do this, we're able to kind of infer what kind of diffusion areas are P or N, simply by using the fact that the majority of the times the PMOS is connected to power and the NMOS is connected to ground. There is also a trick that you can use, especially in this cell here, because normally the PMOS is always bigger than the NMOS for a bunch of electrical reasons. And then comes the important part. We split the diffusions. We see where all the gates are, and we see how they connect with the nets. We can emit two transistors. We go through each split areas that we have, and we emit a list of transistor with the type, if it's PMOS or NMOS, and where the gate, the source, and the drain are connected, which is essentially which shape it touches and which net that is. Once we have that, we can essentially have a list of transistors and how they're connected, and we can reconstruct the pull-up and pull-down network. We do that by doing a float fill. We start from the first PMOS or NMOS connected to power or ground, and we keep expanding our boundary until we find the complete pull-up and pull-down network. And you get the intersection point, which is going to be your output of your domain. You run this over and over on all the transistors that you have, and that allows you to essentially find all the CMOS domains, so all the stuff that can implement a logic gate. And once you have that, you apply the rule that parallel is or, and serial is and. And you emit an abstract syntax tree of the Boolean expression, and that way you instantly recover what is the Boolean function of this thing. And you can even use a property that those are complementary to do like a sanity check if what you found is correct or not. We put everything together. We have a logic expression for each cell, and we have the cells and the wires connected together. We can use this with a connectivity algorithm to just emit the list of cells and list of connections. And with this, we can already emit code, like I showed before. Does it always work? Kinda. For simple combinatorial things like NAND, NOT, AOI, adders and stuff, it works because it's kind of always made on those kind of CMOS domains with pull-up and pull-down networks. It doesn't work with a lot of other stuff. Every time that you have feedbacks, transmission gates, latches, more complicated stuff, we're able to recognize those, but the algorithm says that, yeah, they're there, I don't know what this cell is, because I would have to actually reason about this. And that's where the human comes along, because we are better at this kind of stuff. And for example, the flip-flops are especially complicated because you essentially have a feedback pattern in which one thing feedbacks into another. And inferring those, it's possible by an algorithm, but it's quite complicated. And that's why I said, what if we just give the user some tool to figure out this better? And that's why I built those things to show the schematic. We are able to show the schematic for the single domain and for the single and for the entire cell. The algorithm is kind of simple, it's described here. You essentially start from the top and place everything vertically. And for the logic schematic, instead, we first find all the simple logical expression, and then we use an algorithm called ELK that is the same one used in a lot of other tools to draw all the wires between the things and place them logically. The ELK algorithm is kind of cool. It's Eclipse layout kernel, and it's an open source implementation of algorithm to show those kind of flowcharts. And yeah, so if we see some examples, this is like one cell that we annotated, and we can see already the schematic generated by our tool. This is kind of cool. This is a multiplexer, which is something that takes two inputs and has one output and allows you to select which one you want to read. And you can see here that once you see this, there are two transmission gates, and you can already kind of figure out what is going on. Even if the algorithm is not able to fully do it, the human can. And if you look at something more complicated, like a D flip-flop, the algorithm does a lot of spaghetti, unfortunately. You can still trace it and figure out what is going on, but it is kind of too much. So I wanted to work on this a bit more, maybe be able to manually move stuff around to reduce this kind of crossing. And so this is the result. You're able to go from a fully traced die and annotate the cells and generate your code. And all the combinatorial expression, the simple Boolean stuff, gets translated into assigned statements. And the more complex stuff, we emit a module so that you can implement and simulate it. And this is one cool example in which I was reverse engineering that chip, and this is like a kind of expression for an address decoder. And I was able to figure out that whatever the tool generated actually made sense, and it worked on the full emulator quite well. That was cool. And let's speed run the rest. Drawing wires is still tedious and prone, though. Can we make it better in some way? Yes. I was thinking, what if we try to recognize the vias? The vias, those symbols, those shapes in your chip that have a kind of a very recognizable shape, and you have a via, every time that you go from one layer to another and every time that a wire takes a turn. What if we train a machine learning model to recognize those? And if we recognize the vias, it's also cool because at that moment, basically, we can also recognize the cells. Because a lot of cells just have a very concise pattern that is always the same for what the vias are. So using the vias for recognizing the cells becomes much, much simpler than just doing it on the raw pixels. So I built some tools to do some machine learning annotations directly on the tool itself. You can just place vias with your cursor and define what the rectangles for training that you want to use are. And that way, I basically created a big data set with like 6,700 vias and all annotated so that they can train a model on this. The training was especially fast on this MacBook. It was like 10 minutes of stuff. The model, it's actually a very simple unit, which is an old machine learning model invented in 2015 that still somehow works really well for this kind of stuff. And this is the result. Started from I mean, it's not really visible on the slides, but I should have bumped the brightness a bit. But basically, from a single die photo, it already inferred like 350,000 vias, which was really cool. This is an example of basically what it does. You can see a red spot on each one of the vias, and that is the machine learning model that recognized those. What can we do with this? Let's do a very quick demo. So, when we are drawing the wires, we have a multi-wire drawing mode. If you see here, you can see how this is all the wires all the vias that are recognized. We can go down here, and we can see how we have a lot of those, and we can just click, 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 and click. If we press enter, we can draw multiple wires at the same time, with snapping to vias. And we can see that the moment that those wire ends here, we can automatically stop our wiring so that we can just drag this thing up until the wire ends. And you can see that it automatically, with machine learning, finds this entire thing. And if I have to draw something like this entire bus here, that's going to be incredibly easier than just doing all of the wires manually. If we instead do something like this, machine learning results, we can do snap to vias, and even for more simple wire drawing, we can just be a lot more rough, and we don't have to worry about hitting the center of the wires anymore because we have snapping for that, and that's powered by machine learning. And yeah, it's all those kind of stuff that I built so that they don't have to be in pain with Inkscape anymore. And I try to do the same with wires as well, because if we can recognize vias with machine learning, why don't we use also the same for recognizing wires? It kind of worked, but in practice it's much, much more complicated. And because you can get stuff that is way too complicated even for a human to understand. And the other problem is that the wires can intersect. So it's very difficult for a machine to tell what is actually connected and what is not. And do you want to try the tool? It's on GitHub now. It's very unfinished, and it's very tailored to what I do, which is reverse engineering CMOS gate arrays and standard cells. But maybe someone can find a use for this, and it would be cool. And I left the link here, and if you want, you can just download it. And there is a guide on how you can just start up the different services. And I just wanted to close with what I learned, which is the fact that building custom tool is fun, but this took so much time to build this kind of tool. but sometimes you just gotta do it because the tooling that is there simply doesn't exist. And that some tasks are hard for humans and they're easy for machines, but sometimes the opposite. So might as well find where the human outsmarts the machine and automate everything else. And the last thing is that visualizing those kind of problems is incredibly important, because I would have not been able to figure out all the stuff if I didn't have something that showed me on a canvas where the pixel position of stuff is. So thank you. Thank you. Sorry for taking a lot of time.
Amazing work.
Thank you.
I'm astonished how much effort you have put into it. So, I guess there are questions. Who will be the first?
Why is there a via every time it takes a turn?
That's a very good question. Because I'm not entirely sure, but the reasoning, I think, is that back then they used automated algorithm to throw the wires and to do the auto-routing. And if you keep the rule that everything vertical goes on one layer and everything horizontal goes on another layer, that makes the algorithm a lot simpler. Because that way you know that, for example, if you're drawing a vertical wires, you cannot find anything horizontal or intersecting on that layer.
How expensive is such a microscope?
I don't know, because I normally rely on other people taking pictures. One example is, for example, those pictures here that I'm showing. Those are done by an amazing guy called Infosec DJ. You can find him on social media. And yeah, I think that this setup, it's especially expensive because he had to build like not only the microscope but also the stepper motor to automatically move the chip a tiny bit at a time, and the imaging setup which streams to a Raspberry Pi that collects all the tiles and puts them together. So yeah, those things are expensive. If you want to do it privately, you expect to spend thousands of euros, but thankfully there are incredible people in the community that do this for donations.
Any further questions?
I can do a fun thing in the meantime. I can keep annotating the stuff. If there are no other questions. Let's see it happening live.
Okay.
So we can label our polysilicon. And let's keep doing it. And what is happening here is that I'm drawing those rectangles, but they get merged into a single shape automatically using Clipper. So we define our polysilicon and our diffusion, and we can hide them. We can define our metal, which is this thing here, and here it goes this way and this way. Those are all our power rails, which I'm assuming they're power and ground. And this is the thing here. And this is another. Okay, and let's also define the metal too, since we're here. And okay, now we can define our vias, and we can put the contact vias here, which connect to power. Those that connect to here, and those that connect to ground. And here you have those connecting to polysilicon, so those are going to be the inputs. And here you have those connecting to the source drain and to the other source drain. Okay, the metal one vias should be only those two. And now we define what is power and what is ground, and it's an OR. You can see here how it found like the different nets and where the different transistors are. And it found that those are p-type and n-type. And we can look at the schematic in which we have our PMOS and NMOS transistors. And we can look at the logic in which it just renders this as an OR NOR gate. And yeah, this works for simple cells like those. It If you look at some cell which is a bit more complicated, for example, this is the MOOCs, just tells you that, yeah, it's something, give it yourself a name, but having like a schematic like this automatically allows the user to find how those things work a lot better than just having to stare at this cell here and trying to figure out from this mess what it's doing. Because otherwise what you would have to do here is that you will have to trace this manually, maybe in Inkscape, and then make a list of manually of all the wires where they connect, and then from there draw the schematic. It's so error prone that having something like this, it's tiny, but it really helps a lot.
If no further questions, please allow me a question myself. How do you prove that you've not forgotten anything?
That you're not what?
Forgotten anything.
Oh, sure, I have forgotten a lot of stuff.
But you've covered every wire, every part of it.
So, two things. The first thing is that the approach that I use with this kind of stuff, it's a bit statistical. It's like, I don't care if everything is 100% perfect, because I'm not trying to emulate this. I'm trying to look at the code, and with this, I have an overview of how everything works. And because already from that, you can, this is not an artifact that goes into production. This is an artifact that is used to allow you to have a general idea of how everything is connected internally, and you still have to process this because there are going to be a lot of hidden variables like the delay of stuff and that you cannot know in advance. And the other thing is that we do have warnings. If you look at the reverse engineering cell, for example, stuff, if there is something that doesn't make sense, like if I remove this, it's going to tell me that there is stuff that doesn't make sense. Like you have an incomplete contact, you have some bias here that connects to nothing, and you have an isolated PMOS cluster, which is like that you have a pull-up network that doesn't correspond to a pull-up network. So this is another thing, and the other thing is that also in the die viewer, so in the view that in which you can draw the cells and the wires, when you go into code, you have a lot of warnings that basically tell you if something that you did is completely wrong, like if you have some cells which have some input or output that are disconnected, or stuff like if you have one output on a net, you cannot have multiple. Like you cannot have one wire that has multiple output driving it, because that doesn't make sense electrically. And I mean, here we have a bunch of wires because it didn't finish doing this, but that's the idea. And I kind of implemented a nice code viewer thing here, in which like you have all the problems like in an IDE, and you can also like move between stuff. And this is like all stuff that is not really needed, but it's nice to have. And so that's the answer. Like it's a combination of some things you don't care too much, other things you have the tool that is telling you if you probably did something wrong.
Great, thank you. Giulio, many thanks for a great talk.
Thank you.
Please.